So in my lectures, I've been making the distinction between active matter in a fluid and active matter where you ignore the fluid and just replace it by a featureless damping medium. Today we'll deal with the fluid. So wet active matter. Sounds faintly disgusting. Anyway, let's get started. So what I want to do is to tell you what happens when you really deal with the fact that these particles are in a fluid, and therefore, if you have a particle here and it moves like that and it's in a fluid, it moves the fluid, which affects other particles. This is called the hydrodynamic interaction. You can view this interaction in two very different regimes. One where these things are moving very fast, and if they're moving very fast, then most of what happens is in a little wake behind it. And so I don't mean fast or slow variables, I mean high or low Reynolds number. And I don't have time here to give a lecture on the sort of very strange properties of fluid mechanics when you study it in the limit of 0 Reynolds number. We'll just do an example of the hydrodynamics of an active fluid in the liquid crystalline state when you ignore inertia and only keep track of the slowest part of the fluid flow. Okay, so, and you remember the general picture that we wrote down was that if you ignore inertia, then what happens is that friction times particle velocity, which I'll call P over m, minus fluid velocity at the same location, was balanced by other forces. And those other forces, and the velocity itself obeyed let me just be schematic first. Right, we want to write down an equation of this sort, where, and you can just call this R dot, where R is the position. Suppose you focus on one particular particle, it has position R, and rather than saying that friction times its velocity is equal to the other forces that are pushing it, you take into account the fact that there's a fluid. And you take into account the fact that that fluid, therefore, has to respond to the forces due to the other particles. Any framework in which you ignore the inertia of the fluid and look at the coupled dynamics of particles in a fluid looks like this. Okay? You can write down polymer dynamics like this, suspension dynamics like this, active particle dynamics like this. What changes is the force densities that you put in here, in all these problems. Okay? Yes? All right? So, if those force densities actually come from some pair interactions, then what you will have here is you will have minus the gradient with respect to this particular particle coordinate of some interaction. And here you will just have that same force density coming accompanied by delta functions wherever the particle is. And you solve that problem. And formally, that solution lies in writing U as a linear kernel acting on these forces. You tuck it back in here. And obviously, in general, you get a complicated equation for R. And then for different particular physical settings, there are different tricks you do to solve that problem. Okay? All right. Now, we want to do that specifically for an active liquid crystal. And you remember that, let's take the particular case. Remember, I developed also a general framework for writing down active dynamical equations. I said if you have some abstract coordinates q and some abstract momenta p, then you could have a dynamics like I wrote down equations which schematically look like this. And after I went through this process of eliminating the chemistry in favor or eliminating chemical dynamics in favor of the chemical force, I ended up getting what looked almost like just to be consistent with my notation last time. And so what was new here was this. And I said that this is a license to write down active equations for active anything if you know the equations for the non-active version of it. Note that when I wrote this equation, this problem down, I didn't treat H as the microscopic Hamiltonian because I even allowed the coordinate-like degree of freedom to have a relaxation. So H should be thought of as that object which, when you switch off active processes, gives you the equilibrium probability distribution function. It's actually just minus kt times the log of the steady state distribution function. In this description where you're using the equilibrium problem as a takeoff point. So I'm pretending that that part of the dynamics is somehow left undisturbed. It turns out that's fine. Okay, you can do that, or you can say that you can use the same kinds of arguments to modify these terms, to write down these terms. Okay, so that's the limit in which we're working, and that's good enough for absolutely everything we're going to do in this lecture, for example. Okay, so because H is an effective Hamiltonian that gives you the probability distribution, I, in general, will have a damping and a noise even for this Q coordinate. Okay, so I want to apply this to the particular case where instead of Q, I'll consider a system of elongated objects. And for simplicity right now, let me think of them as not having a polarity, only an axis. And therefore, I'll describe them by a traceless symmetric tensor. Their configurations by that. I will, for the most part, not worry about their concentration. Let me pretend somehow that concentration is kind of uniform, and I'll ignore those fluctuations. And I will keep track of the momentum density field of the fluid, which is of the total system, particles plus fluid, which I can write as the mass density into a velocity field. Okay, so orientation field. Sorry, let me use this notation. Instead of P, I'll use G or U. It's often convenient, since this is a momentum, I want ideally to work in terms of momentum density, because if I have momentum conservation, it's most conveniently expressed by saying rate of change of momentum density is the divergence minus the divergence of a momentum current. Momentum current being an object which you've seen in various forms in other lectures, a stress tensor. Okay, and so what we want to do is write down equations for this guy, and this guy, and we want to use this principle to invoke the mysterious extra term. Okay? And my claim is that I know in general the minimal form of this extra term. The reason I know it is I want to write down an equation. So I'm going to write down an equation for Q, which I'll come to in a moment, and I'm going to write down an equation for U. Equals various things. There'll be a pressure gradient, there'll be viscous damping, there'll be stresses coming from the fact that this system has an orientation field. Okay? And there'll be noise, which I, for the most part, won't worry about today. Because I'm thinking of a bulk fluid, its momentum can't go anywhere. Therefore, this noise is a conserving noise, so it's the divergence of a random stress tensor. Every term in this equation has to be the divergence of a second rank tensor. This is also, but I won't worry too much about this right now. What I'm going to do, okay, so I can write this down. Yeah, let me have it written down. Why not? I'll tell you why these equations have to have the form they have in just a minute. Not giving myself enough space here. If you don't mind, I'll move this to the left. You don't have to erase your notebook stuff if you're writing. I hope I've got these signs right, but anyway, if I haven't, I at most got them wrong overall. I'll tell you what these guys are in a moment. Don't be too intimidated by the complicated form. Actually, it's fairly simple. And I'll tell you what that means. Plus its own noise. Okay, so I'm trying to say that this becomes this, although it looks rather more messy. And this becomes this, okay? Q being an orientation field it's a configuration variable. It's a t going to minus t symmetric variable. U being a velocity field is, or G being a momentum density field is odd under time reversal. So these are those two kinds of equations that I'm writing down. So it's just in this form. This complicated left-hand side is because I want to write something which is material frame invariant. I want to write it co-moving and co-rotating with the fluid, with the medium. So omega is the antisymmetric part of the velocity gradient, and kappa is the symmetric part of the velocity gradient. This whole left-hand side is just expressing the fact that you want to write this in a way. This is the co-moving, co-rotating derivative. And this additional complication of co-rotating comes in because this is not something you'd worry about if it's a scalar, but because Q is a tensor, you have to deal with this. This bit, so this whole side is purely kinematic. This, if you like, is what stands in for the Q dot. Sorry, in case I missed the dot there earlier, there it is. Okay? This bit is the rest of the reversible coupling of Q to the velocity. Okay? It looks complicated, but all it's saying, remember, what's the symmetric part of the velocity gradient? Supposing you have a spatially varying velocity, grad U, I can write that as kappa plus omega. You agree, right? If I add these two, I get grad U. Okay? So if I have, a velocity gradient can be turned into a pure rotation and a shear. So this bit actually tells you, so imagine I have a flow like this. I can resolve it into a rotational bit and an extensional bit. Right? And this guy tells you about this bit. And the reason, therefore, that this term arises is that if you've got a bunch of orientable objects in a fluid and you impose a flow like this on them, then if you put orientable objects in there, they're going to have a tendency to align with the flow if they're elongated. Okay? So what that says is that the symmetric part of the velocity gradient acts like an orienting field for the orientational order parameter. And that's why it has this form. This bit can be argued for by saying that the degree to which it orients eventually starts to depend on the fact that it's oriented. Okay? Another way of viewing this whole thing is to multiply both sides by a viscosity and then view this viscosity times this thing as a viscous torque, and viscosity times this guy as saying right? Yeah, as an aligning stress. Okay? But you don't have to. There's more than one way of viewing it. I prefer the first way. All right. This is this bit, relaxation. Right, so you have some free energy functional. in the absence of imposed flows, the Q wants to relax either to 0 or to its favored equilibrium value, depending on whether you are at parameter values where the equilibrium state of the system wants to be aligned or isotropic. So this does that. And this is the noise corresponding to this guy. Okay. So if we were doing a pneumatic fluid at fluctuating around equilibrium, this is what you'd write down anyway. Now, okay. Second bit. This is the equation of motion for a fluid about which I've talked reasonably often. This is the material derivative. This is pressure gradients. This is viscous damping. And this is everything that the orientational order parameter does. Okay. If it is a thermal equilibrium system, what would happen is this would contain corresponding to this. Remember, viewed in another way, this part of the dynamics comes from Poisson brackets between Q and P, as does this part of the dynamics, right? Likewise, this part of the dynamics, actually, this part too, comes from the Poisson bracket between Q and the velocity field, as does this part of the dynamics, if I didn't worry about the active stuff. So there's going to be a piece in here with all these lambda zeros and lambda ones. But we're now going to use, and that would be like you've got this piece and you've got right, this and this. Okay. Now we want to know about this. I've lumped both this and this into one term here, which I'm calling the stress coming from the order parameter. And what I'm going to say is that, therefore, sigma q is stuff from the free energy plus the extra piece. Right. So I can write down the stuff from the free energy, but it's a bit of a mess. Roughly speaking, because the derivative of the free energy functional with respect to Q, I'll just quickly write it. I'll write it down once and then never write it down again. This bit is so it's basically as though the derivative of H with respect to Q was like a local stress. Slightly modified by the fact that you've got this additional term. Okay, roughly speaking, what it says is that supposing we had a system at equilibrium. Equilibrium for the Q order parameter is del H over del Q equals 0. If del H over del Q is 0, then even if the solution to del H over del Q equals 0 is a non-zero Q, the corresponding anisotropic stress is 0, right? Because we've said the stress due to the order parameter, if it comes only from the effective Hamiltonian of free energy, is proportional to the molecular field conjugate to Q. Equilibrium is molecular field equals 0. So you can have a state of non-zero Q, you can have an aligned state. The corresponding stress tensor will still be isotropic. So a liquid crystal in its ordered phase at thermal equilibrium, a pneumatic liquid crystal, is aligned. It has a uniaxial structure, but its pressure obeys Pascal's law. Its pressure is isotropic. The anisotropic part of the stress is 0 at equilibrium. Okay? That's what this says. What does this say? We have to now guess. We have to now use our, that we are empowered to write this term down. We know it's going to be some coefficient saying how you're holding the chemistry out of equilibrium times some allowed dependence on the Q tensor. Okay? So I claim this thing has the simplest thing I can write down, and since it's the simplest, you have to tell me some good reason why I'd rule it out, otherwise it's there. It's got to be something just proportional to Q. So this sigma 0 contains the chemistry and the off-diagonalness of the Onsager coefficient. All that is buried in it. So gamma 1, 2 of Q over gamma 2, 2 times, so like, gamma 1, 2 of Q times the chemical velocity, which is this guy over that guy, is sigma naught times Q. Why do I say that? I say that I have to write down the minimal object that I can write down. It's got to be a stress. It's got to be built out of Q. What can I do? This is it. Okay, if I had a polar order parameter, supposing I had a system made of orientable objects with head tail was different and which had some possibility of aligning in such a way as to respect that 4-half difference, then you could build a piece out of P. Let's say there's a local order parameter P, which is the local average of the little n's unit vectors carried by each particle. Then I could have something, you know, I could have something else. There's two ways I could make something second rank. I could make something bilinear in P, which is not seriously different from this guy, or I could make this bit. This bit, even though it involves P's, has no sign of the difference between forward and back. It's, you know, this is invariant under P going to minus P. This, on the other hand, is not. So this term is polar. So for a polar system, this term should also arise. Okay? So what we want to do is to take these somewhat complicated set of equations. They're technically complicated, but conceptually they're just what I told you. Okay? Continuum mechanics of an orientable fluid augmented by this guy. And see what happens. So at some level, actually last year I was talking to Tom Lewensky, and he very kindly told me, although he was very nice about active matter, he also did tell me that one of the reasons that so many people are doing active matter is that you can take whatever you're doing and add some active to it. It's like he didn't say this, but he indirectly said it. But in my mind, it's almost as though it's like a seasoning. You can take whatever you're doing and add. So this is the downside of active matter. It's easy to do. Okay, because all you do is you take what you had, you add this term. Now, of course, if you're wide awake here, you'll start worrying. You will say, look, this term is proportional to Q. What is H? What is H? I didn't tell you in detail the form of H. H is, at this level of description, H is just, you know, Ginsburg, Landau, Dejean. Functional, by which I mean that it'll have some Q squared term, it'll have some, I wrote this down last time, term, or some general polynomial in Q, and it'll have that Q term, etc., maybe some coupling to the density, etc., right? So you will tell me, if you're really on the ball, you will tell me that I can generate this term from here by just shifting this coefficient. Right? Nothing new about that term. It's actually there. It won't be there if you okay. So I'll tell you the real secret. The point is, if you shift, the real meaning of that active stress term is not that you get a term proportional to Q here, which is not in general. The real meaning is you can try to shift it here, but you can't shift it the same way here and here, because I didn't tell you how to modify this equation by activity. Obviously, I have to add allowed terms to this equation. What allowed terms will add to this equation? I'll add something, again, proportional to Q at the lowest level. And there's no reason why this shift and this shift have to be equal. Generically, if you write down these equations on phenomenological grounds, you can add a term like this here, you can add a term like this here, except if you tune parameters to some special point of coincidence where everything fits. It's not an effective equilibrium description. So the truth about the active stress is not that you can add it to this equation. Like any deviation from equilibrium, it's a breaking of detail balance, which in this language means that you can't change a coefficient in one place and not change it in the other place. That's really where it's coming from. Now, this is not an Onzaga symmetry, because this is a dissipative term, this is some weird kind of reversible term. That's not really what I mean. What I mean is just that you can't compensate it by redefining your energy. Okay, so what you can do is you can say, I'm writing down this equation with an H which has already had that shift done. And I'm defining my ordered phase, the state, the reference state of Q, by the steady state of this equation in the absence of flow. So this H is not even really the original effective Hamiltonian or effective Ferenczi functional for the problem. You've already done a little bit of shifting around, because you take any problem and you do a little bit to disturb it a little bit. Take a critical point system and shake it a little bit with your hand. You'll probably achieve a TC. Meaning that not every departure from equilibrium changes the problem radically. Some departures from equilibrium are irrelevant. They just take your original phase diagram, move things around a little bit, don't change the topology, don't change the scaling, but shift TC. TC shifts are what we don't really care about, unless they go to 0 or something, right? Okay, so having said that, now we'll say that we'll assume that H, by convention, we'll say that this is what I mean by H. And if this is what I mean by H, generically, I get a Q term here, which can't be wished away. In particular, supposing this is a continuous transition as displayed here. As I approach that transition, Q's relaxation time will go to infinity. The coefficient of Q in this equation won't vanish, which it would if it had come from the equilibrium thing, right? And so many interesting things happen. Okay, so is this completely, I've spent a long time on this just to also to tell you that, again, this is not just a mechanics problem. It actually is a statistical mechanics problem at heart. You're breaking detail balance, and that's why you're getting all this. Okay? Any questions before I go further? Yes? You need noise. The point is, yeah. So reason is just that supposing, it's no different. Okay. When in equilibrium dynamics, whenever you introduce damping, whenever you introduce relaxation, there has to be an accompanying noise. Because this, now forget about activity. Imagine this is some abstract coordinate, some abstract momentum, and they are governed at thermal equilibrium by e to the minus h of q and p. And if I introduce this term. If I introduce this term, then see, both this and this are producing some diffusion in QP space, right? If I abolish one of those two diffusions, I'll be in trouble because the current due to this bit won't be compensated by a diffusion current due to that. It's the old, meaning that if you go back, take this problem and write down the Fokker-Planck equation. If you want e to the minus h to be the steady state, if you put this in, you had better put in the noise here, because this noise will give you a current proportional to the Q gradient of P. So it's always a Q gradient of P balancing P times the Q gradient of the energy, right? That's all it is. Neither of them is active noise, right? Okay. Again, full disclosure. Remember when I derived this, I said, look, we're doing this slight shift from thermal equilibrium. We're assuming that X, the chemistry, enters only through this part of the problem. So what did we do? We formulated a problem of the thermal equilibrium of Q, P, and X. We then held the force driving X by hand to a non-zero value. That's our friend delta mu. And we pretended that X didn't enter anywhere else. So all we had to do was replace X dot in the momentum equation by this expression, and a little bit of reshuffling and such like. But we were pretending in that whole process that H didn't contain X except as an additive term which goes away when you differentiate with respect to Q. Right? We're saying there's an H of QP and some X stuff in such a way that when I take del H over del Q or del H over del P, I don't worry about X. I can probably do better, but for the purposes of this derivation, that's all. I also pretended that the noise was unchanged upon holding delta mu constant. Now, what that means basically, remember, this whole formulation comes from a thermal equilibrium picture. There's no guarantee once I start pumping ATP through my system at high speed, there's no guarantee that the noises driving these variables remain the same. Take an extreme example, when I have rods lying on a table and I'm vibrating it, the only noise in the system is the noise that's there because I'm shaking the system. So in that extreme case, the noise is actually the driving. So you can imagine cases where this picture fails kind of badly at a quantitative level, right? So that's the extreme. Those rods have no random motion except because you're shaking. So I just want to work out three consequences quickly, and I think I can do it. And I think the first thing I want to do is to explain why a term of this sort is highly plausible if you go to the microphysics of self-propelled particles. Okay? So, I've been talking the language of liquid crystals. That means if I have a suspension of bacteria, I'm taking the bacterium, the orientation field of the bacteria. But what is it that the bacteria are doing that's producing a stress proportional to orientation? So it turns out to be very simple. And it turns out that in a different language, slightly different fluid dynamics people knew it at least since the 1970s, maybe since the 1950s. But they didn't write it in terms of liquid crystal hydrodynamics. So we get credit for maybe re-expressing it in that language. First of all, swimming is force-free. What do I mean by that? It doesn't mean that you don't have to do any work when you swim. I only mean that you plus the thing you're swimming in, neglecting buoyancy effects, are taken together a force-free system. Swimming is not somebody exerting a force on you and making you move. You and the fluid do something and you move, right? So, to take an example, here's a bacterium swimming. How does it swim? So this is a bacterium. It pushes fluid back with its tail and its body moves forward. And here's the other, all microorganismal swimming people's other favorite organism. It's an alga. And this thing pulls fluid towards itself and its body moves forward. So, it pushes that way and moves this way. So both of these, so when I say force-free, what I mean is, one of the consequences of that is that if I want to include swimming in the Navier-Stokes equation, it's not an external force. It's some complexion of forces which add up to zero. Now, if you have a force density which when integrated over space adds up to zero, what that means is that it must be the divergence, it's a momentum conserving arrangement of forces. So it must be the divergence of a stress. So we should be able to go from this picture to this picture. And actually it's very simple. I'm, maybe laboring the obvious. Yes. Excuse me? This doesn't assume that. This assumes that. If the fluid wasn't Newtonian, I would have to either write a complicated expression here or introduce some other degrees of freedom. In fact, at some level, the moment I introduce this Q field, the fluid is really no longer Newtonian. Why? Because the stress, forget about active things and swimmers. The moment I introduce this other degree of freedom, one piece of the stress is something linear in Q and its gradients, and Q has a relaxation time through here. So that time might be quite short. If it's a fluid made of 20 angstrom long molecules, the viscoelastic time isn't very big. But you could take the same if you take a fluid, it could be a fluid made of 1 micron rods, a suspension, I'd say, made of 1 micron rods, in which case that time is quite big. So you can use this. Many of the properties of standard rheological models can be reconstructed from this as well. Often when they do that, they introduce, when they do fluid dynamics of, various people's favorite rheological models, you do introduce what they call a conformational stress of some other degree of freedom. Q is not very different from that. So you see equations of this sort in many guises in the viscoelastic literature. Okay, so now what I'm saying is if you just take this picture and say that really what you have is a pair of point forces. You've got one force here, strength F. You've got an object, let's say with its body center here. I'm not being very precise about what I mean by that. And let's say that distance is A, that distance is B. And this axis is a unit vector N. And that position is R. then clearly this pair of force densities of one such particle is just, it has a magnitude f, and it is two, in this simple, really elementary picture, it's the sum of two delta functions, one situated at r plus an, the other at right? Everybody agree with this? Why do I write point force densities? I want to write something which, when integrated, is a force, right? Because I want to write something, and I want to have something that comes into the right-hand side of the equation for the momentum density, the rate of change of the momentum density. So it's a force density. The force density in this simple model, if you like, this is a simple model which averages over the actual stroke of the organism. Right? Actual swimming is generally a periodic process whose net result is a translation. But the corresponding force, if you don't resolve the time scale of that process, is this kind of force density. Okay? And in general, you have to think of it as two asymmetrically placed forces, because, if you like, to use a joke that we used 13 years ago in that paper, there are movers and shakers. Okay? If this point is, if A and B are equal, then this thing will disturb the fluid, but individually it won't get anywhere. By symmetry, which way can it swim? So A has to be not equal to B. And you can now expand this, and maybe I'll expand it up here, over here. So if you expand it, let me get all my factors of minus and plus and things, right? So first of all, what do I want to do? Just whenever I build whenever I build cosecant equations, I want to have something at the particle level and then sum it over all the particles to get the field, right? So this is the one particle force density, and I want to build the collective force density. So clearly, if I call this, F vector I want to sum the total force density, divergence of sigma active is sum over I of all these guys. Right? Divergence of stress is a force density. And you can do that sum. And you can do that sum, but you can also expand this. Okay? Why do I want to expand it? Well, actually, when I expand it, I'm ultimately just doing a gradient expansion. You can see that if I expand, what am I going to expand? I'm going to say it's delta of R minus Ri minus this guy, which is delta of R minus Ri minus this guy times one gradient, a product of these guys times two gradients, and so forth. Right? So what will I get? I will get, and so forth. I think that's correct. Yeah, because you'll get an A squared from here, and you get a B squared from here, so I can write this A plus B A minus B, and so forth, right? And so the force density and there should be an F here, strength of the force. This is Fi. I'm missing something, am I not? Yeah. There's got to be a vector to begin with. So, then I lying around here. But this whole thing is a scalar. This is the force acts in the n direction. Okay. These are not dotted. This is Ni, Ni. I'm reasonably confident that I've got all the factors right. Okay. And I'm just taking the trouble to do this because we wrote down an object like this just the other day. The sum over all particles of nn, delta function of each particle. This, if you take out its trace, if you make this a trace-free part plus a pure trace part, the trace-free part is the nematic order parameter times the number density. Right? Therefore, what I've done, and this I'll come to in a minute. I'd like to keep this, so maybe I can write here, right? Yes, no? Huh? Yeah, thank you. Not here. Huh? Till this line, right? Draw the line somewhere. Yeah, okay, fine. Okay, so what have we got? What we've got is, so let's just look at this piece. This piece is actually the Q tensor. So this should be a function of time in general. These guys all are functions of time. Unit tensor times the number density field. I won't use rho because I've used rho for the total density field. So I'll use C. Right? When I do this nn times delta, what I get is not the local average of the nn's. I get that times the local number density. Right? C times Q is also what I called W in yesterday's lecture when I was talking about the nematic case. It's a tensor density, not a tensor. Okay? So what does that give me? This, the great thing is I've actually, in this particular microscopic model, I've shown you what this guy is and I've shown you what sigma naught is. Sigma naught is this force times this length times the mean concentration. Right? In that description, I didn't worry about the fact that, I assumed a medium that is suffused uniformly with activity. Actually, if activity is carried by particles, if there are more particles here or less particles here, that changes the local level of activity, assuming each particle carries a fixed level. This takes that into account as well. So if you like, you can say that this sigma naught is times C naught. C naught is mean concentration of active particles. Active particles being the swimmers in this case. Okay. So at least it tells you, the reason this is reassuring is just that it's always nice to know that what you argue by by intimidation on general symmetry grounds actually turns out to be true when you pick an elementary microscopic realization of it. I'll say a little bit about the next term. If you look at this, obviously now there's some, you have to decompose it. This is the same moment story. Totally. Look, I'm saying that, look, I took a bacterium and I replaced it by this. In doing so, I wanted to write down the minimal model in terms of point force densities that could reproduce the flow field around a bacterium. So I know that the forces have to add up to 0. I know that if A and B are equal, this bacterium will never get anywhere. So therefore I should have A not equal to B. What sorts of numbers would I put in? For F, I'd put in the typical thrust of a swimmer. For A and B, I'd put in some typical dimensions. Now, if you ask me whether I should put in the body size or the flagellar size, what you really need to do then is detailed modeling to figure out what force dipole model corresponds to what swimmer model. They're equivalent and they can't but be equivalent. But the actual values, you can say that, for the typical organism, these A's and B's are some micrometers in size. F, what is the thrust that these things exert? Oh, no, it's probably not piconewtons. Piconewtons is okay for molecular motors. It's probably nanonewtons. Am I right? Probably. I mean, to put in numbers, I mean, a crude, not totally accurate way of estimating is just imagine you had a sphere of a few microns in size moving at a few microns per second. Estimating the drag on that will roughly give you a number. It should be good within a factor of order unity. Okay, so that's justified this approach. I was just going to say that if you look at the next order term, the first thing you can do with it is replace this NN by the unit tensor. So, I mean, if you expand this out, there's going to be this guy times unit tensor, this guy times Q. I mean, so if I replace this by the unit tensor, then this is just the polar order parameter. It's the local average of N. I'm saying if you write this in terms of moments, the first term you get won't be the third moment. It'll be the first moment times an isotropic bit. So this means that the force density is 2 grads contracted with this guy. 2 of these, if I make them unit, will make this del squared. So you'll get del squared and grad div of the polar order parameter. So you'll get this piece. And this piece, sigma 2, is something like, I shouldn't even call it, I mean, sigma 2 doesn't have units of stress. Sigma 2 has units of, if that's a stress, then that's a stress times a length. Why? Because then A plus B times an A minus B. So at least it justifies these general forms. This is important because if all you had was this, you wouldn't swim. But it's also true that the far field, if you co-move with the object, the far field is dominated by this. Why? Because this piece has fewer gradients. So the completely long wavelength theory of these things is dominated by the flow field due to the force dipole, not higher multiples. Okay, so there are some fun consequences of all of this. So now we can, having sort of justified our coarse-grained theory in terms of a microscopic picture, we go back to the coarse-grained theory. And that coarse-grained theory really, so there are several predictions that come out, which I'll write here. I'm just writing it to have it somewhere. Globally aligned states turn out to be unstable. Globally aligned states in an unbounded system turn out to be generically always unstable. If you take an isotropic phase and ask, is the viscosity of the isotropic of a fluid with a bunch of independent swimmers, is that viscosity different from what you would have if you killed the same swimmers but kept their bodies in the fluid? To put it sort of appealingly. And third, imagine you've got a fluid with a bunch of swimmers swimming more or less independently of each other. Is the velocity field they generate random? You might think, imagine you've got a dilute suspension of completely independent run and tumble swimmers. Just, it's uncorrelated. What kind of velocity field is it? All these three questions, all these three turn out to be quite surprising. Okay? And let me do one of them at least in some level of detail. So supposing you say that, so what you do is the following. Take these awful equations. First, let everything be spatially uniform, and first and switch off activity, switch off everything. Okay, you just got del H over del Q equals 0. Choose parameters in H such that the system wants to be aligned. So choose within this mean field picture, let A be less than 0. As I said, really I should have a Q cube term as well. You can do all that. You know, choose parameters such that the the stable solution is Q not equal to 0. Cinematic. Okay? And let's diagonalize that. The reference state. Let's write it as a two-dimensional analysis suffices for everything I'm doing here. Okay? And now I'm going to perturb it. And that perturbation I can write as just expanding sines and cosines of 2 theta to first order. That's enough for my purpose. And all I want to know is, what's the equation that theta obeys? And I want to work in the approximation that I completely forget inertia, acceleration, etc. And by the way, for the kinds of systems you're talking about, that's perfectly okay. If you put in numbers, Reynolds numbers, that's fine. Okay. So what you're going to be solving is this equation. And the thing to note, and okay, what happens that makes the problem sort of zeroth order treatment of the problem very simple is that activity comes into this term just as div q. Elasticity, okay, let's think a little bit about what will happen. Go back to either the equilibrium pneumatic or the equilibrium XY model or whatever. Supposing you were solving the equilibrium XY model dynamics, you wouldn't have all this stuff. You'd have d over dt of an angle, and you'd have the derivative, you'd have ds over dt equals minus del h over del s. And it's true that h contains s squared. Supposing you didn't do a fixed length spin, do a soft spin XY model, you have an s squared, s fourth, and grad s squared. Just like I've got a q squared, q fourth, and grad q squared. When I do that, of course, I'll get some dynamics for the length of s. But when you look at del h by del s for small fluctuations about the ordered state, those terms contribute nothing. Only the del squared s contributes something, right? So you end up getting d theta over dt is k del squared theta. And we discussed this yesterday, and other people have talked about it and so forth. In the same way, what will happen here is, so what that means ultimately is that when you do del h over del q, whether here or here, for small fluctuations, the only thing that will end up contributing is the del squared q stuff. But now you have this. And remember, we've done this sort of revised thing where we've said h is the thing that comes in here even after you fold in various exact terms, active terms. So we redefined our h, so the reference state we're talking about is the state where this guy is 0, right? So this extra q piece just stands here. So what that means is that this velocity equation will be plus higher orders in gradients. Okay? Schematically, so all the stuff from the del h over del q terms here come in with lots of gradients. Okay? And what does this equation look like just schematically? Ignore all these details. That's a grad u. That, again, perturbations of that will involve grad u because you'll put the velocity. Remember, the reference state is everybody pointing the same way. and velocity is equal to 0, fluid velocity equal to 0. You perturb it and look at the velocity, you look at the angle perturbations and the induced velocity to first order in those angle perturbations, right? So reference state is u equals 0, q equals, so I should set this. Q equals this guy, and u equals whatever, some small. That's the perturbation. Reference to, so u equals 0 plus u equals 0 plus u. U is a first order quantity, theta is a first order quantity. Okay. And which is consistent with what I'm writing here. So when you do that, this bit, for instance, will be something like, in terms of power counting, it will be 1 grad on a U times the reference state. Okay? As will this. As will these. So what you end up getting when all the chalk dust settles, which I don't want to spend all my time doing the algebra on that, is that if you solve this equation, how do you solve this equation? You invert the Laplacian. Sorry, I should always say I'm working with an incompressible fluid. Incompressible doesn't mean that the concentration of the particles can't change, although here I confess I'm ignoring the concentration as well. Incompressible means the total velocity field is incompressible. The total density, particles plus fluid, can't change. Okay? You have to say all those things very slightly more precisely if the masses of the particles and the fluid, the solid particles, the fluid particles are different. Assume that everything is made of the same thing, but there's just particles. Okay? So incompressible as a whole. So if I do that, I have to invert the Laplacian. I have to eliminate the pressure by taking the transverse part of this. It's just algebra. But schematically, what you can see is this bit will be one derivative on an angle. And so, and what comes up here is some things involving one derivative on u. So the net result, things with one derivative on u are things with no gradients on the angle. Right? So you'll end up getting terms proportional to theta and terms both from here and from the elastic stuff here with 2 grads on theta. Okay? Some effect, either the original Frank constant, a mildly modified version of it, times del squared theta. And the coefficient, what will the coefficient here be? It will be, it's an inverse time. So it's going to be sigma 0 over eta. Right? A stress schematically. So the effective dynamics of my system in bulk will be like this. Now, of course, I've been wildly schematic. I haven't put in direction dependencies. I haven't put in the fact that there are all these non-dimensional flow alignment coefficients. So there'll be some number here which depends on those coefficients. And there'll be a cosine of there'll be some numbers times something like cosine of 2 phi, but I'll tell you what I mean by phi. In fact, let me work directly in Fourier space and say, call that directly, okay, where phi is the angle between the wave vector that I'm looking at and the ordering direction. And I haven't said if this is positive or negative. Clearly, it changes sign as you go from above 45 degrees to below 45 degrees. So if you go through this more carefully, what you will find is that what you will find is that generically you can think of two kinds of perturbations, right? Let's say the axis is on average like that. You can think of perturbations like that, which are bend, and you can think of perturbations like that, which are splay. And for one sign of sigma naught, the system is unstable to this. For the other sign is unstable. So what's the instability? It's wherever, times theta, excuse me, at wave vector q. The instability is wherever this coefficient becomes positive. Okay. However, there's always this to compensate. So it's only at long enough wavelengths that you get this instability. The mechanics of this instability, and now it's really mechanics. The mechanics of instability can be seen very easily by considering a geometry like this. Let's say you have a channel, and let's say you have all these guys on average aligned like this, and so the reference state is everybody pointing like this. Now imagine a perturbation where it's pointing like this at the walls, it's pointing like this in the center and smoothly interpolating, and pointing like this again at the walls. This distorted configuration is going to give rise to fluid flow. For the polar case, that fluid flow is like this and like this. The result is that you perturb these guys like this, and the flow pushes them more in the same direction. That's actually all there is to it. And ultimately, it's just a consequence of the fact that you've got a bunch of aligned things, and you're putting them under tension. And Euler, or you could take the other case if you had pushers and you have them aligned, and you're putting them under compression. So you know that a macroscopic uniaxial compression makes things buckle this way, and a macroscopic uniaxial tension makes things buckle this way. So if you take, I don't have a polythene sheet here, if you stretch a sheet, you get buckles like this. Right? This way, yeah, if you stretch something, you get buckles like this. If you push, you get buckles like that, whatever. Yeah, so this is actually, in some weird way, it's like a general buckling instability. Okay, so I won't say more than this. The main thing is that if you do it in a channel geometry, clearly the strength of the activity has to be large enough. Otherwise, elasticity will defeat it. Okay. The other interesting thing is it's not just an instability to a buckled state. This is an instability to a state of spontaneous flow, because this instability is held in place by the flow that it generates. So that means these are self-starting flows. You have something in a channel, you turn up the activity by whatever means you like, it'll just start flowing all by itself. It's not violating any rules, you're feeding it energy. So, it's not something for nothing. Okay, so I'll tell you one, I won't tell you about the viscosity story. Let me tell you about these long-range velocity correlations, because that's very simple to explain, and then I'll stop. So, the reason I went through this is that sometimes non-equilibrium physics doesn't change the fluctuation spectrum. It actually, it doesn't change. Sometimes the reason a state is unstable is not that its noise-induced fluctuations somehow have the grow with system size. It's just that your conjectured reference state is simply unavailable. It's not even locally stable. So you start with these equations, you find you find the global minimum of the free energy, you introduce just homogeneous driving, and all of a sudden what was earlier stable is now unstable. So that reference state is no longer a reference state. So a way of looking at it is, this is all the equilibrium directions. You have a system, you've got a free energy, so you perturb it in any of these equilibrium ways, it's stable. There are other directions, you can add other axes, and in some of those directions, it's immediately unstable in the infinite size limit. So another way of viewing it is to say that these systems are best thought, if you want to think of a stable stationary state with this kind of order, you should confine it in at least one direction. See, for example, here I drew a channel geometry. You could instead take a 3D system and confine it between two plates in such a way that these filaments now can point anywhere in the plane. You increase the concentration enough, you get an aligned state like that, and you can look at the dynamics of that aligned state. And that's a perfectly good two-dimensional liquid crystalline system. Bulk systems with momentum conservation sorry, always unstable in these cases. So you can't really talk about a 3D ordered active nematic as far as I know. So just one fun thing. So long-range velocity correlations. Let me forget about all this complicated equation. Let me write down a very simple model. So supposing I write down my momentum equation, once again, let me ignore inertia. And remember, I wrote down that complicated equation for Q, but if I just linearized it, all I really had was that Q, okay, supposing I'm in the isotropic phase, okay, so I don't have a free energy functional that's making it order. I have a bunch of independent run and tumble swimmers. So I've got these things that swim for a bit and then forget their direction, swim like that, and then forget their direction, swim like that, etc. These objects, of course, the fact that they have a swimming direction means that they carry polar as well as apolar stresses, but doesn't really matter. It doesn't change our story any. And you've got a bunch of them, and they're more or less independent of each other. Okay, let's ask what kind of correlations would this noise set up in the fluid? The answer turns out to be surprising. Let me, for the moment, keep inertia at the level of unsteadiness at least. I won't keep u dot grad u. Let me just keep this. Okay, and this picture means that that means I can think of my Q field as a spatially white, temporally colored noise. It's a model. I'm saying, strictly speaking, I should see what the fluid velocity does to these guys and so forth. But at the moment, supposing I've got a bunch of swimmers which have minds of their own. They respect momentum conservation, and therefore they enter the momentum equation only as the divergence of a stress field. Okay, but each of them has a built-in controller that it resolutely ignores what the rest of the fluid is doing, and tries to swim in some direction, but loses its way. So this will be some number times delta of r times e to the minus . Why do I do this? This is a way of putting in motion with a persistence time tau. I could put it in by different ways, but this is good enough. Why do I do this? I'm saying they're completely uncorrelated with each other. So the stress field they produce looks like this. And this is just the strength. You can very quickly see. So first of all, if you can see immediately that this cannot be an equilibrium fluid. Why? Because the damping is local in time, the noise is colored. Okay? Damping has no memory here. Colored noise. And so you can see that, yes, white noise is noise whose spectrum is completely flat in frequency. This guy won't be. What's the Fourier transform of an exponential? What's the Fourier transform of an exponential? Quiz time. It's a Lorentzian. And that means it has different weight at different frequencies. Right? It goes from constant to 1 over omega squared. So you call it colored, you call something white because it has all frequencies, and therefore if it's not white, you call it colored. Because it's got different frequency, different weight for different frequencies. Yes, because if it is delta function in time, then in the Fourier domain, it's flat. And then you call that white. And so it's just very easy. It's just educational to calculate the velocity correlation function. So what do you have here? You've got that you can see that let's Fourier transform in space and time. Times the noise, right? What are we calling that? So the UQ omega mod squared dividing by suitable factors of volume and time is going to be the product of two Lorentzians. Let's hope I can do this without algebraic mishaps. Yeah, so what I'm worrying about here is if I've got this bit right or if I have some... do I have a tau upstairs? What do I have? I want this at t equals 0 to be 1 over tau. That means I want the integral of this. I can never do this right. I want this guy at t equals 0 to be 1 over tau. I have to do it that way? All right. Somebody will have to tell me if I have a tau or a 1 over tau upstairs. I probably have a tau inverse upstairs, right? No, I think let me write it this way. I like it. If I try this, then maybe it'll turn out okay. And then I have to have a tau inverse. No. Then I'm okay. If I do the integral over omega of this, what do I get? I get the width, which is tau inverse. Yeah, this is good. There may be a pi missing somewhere. Yes? Am I missing anything? Because this has the property that at 0 frequency, I think this is fine, apart from maybe some pi somewhere. All right, why am I going through this whole rigmarole? It's to point out that the velocity correlator in Fourier space is the product of two Lorentzians. Okay, and that means what that means is if I want to calculate the velocity equal time velocity correlator, that's the integral over omega of that guy. So you can, of course, you can do it. You can do the integrals. You can do it by partial fractions, whatever you like. It's very easy. But it's instructive to see what's really going on. You've got a Lorentzian, a fat Lorentzian, and you've got a skinny Lorentzian. Okay. Clearly, for Q going to 0, this is the skinny Lorentzian. Right? Let's define Xi to be then for QC small compared to 1, this is the skinny Lorentzian. And this is the skinnier one. So supposing I'm working in this regime, then I can simply set omega to 0 here. This integral, this term dominates the integral, and I get a 1 over q squared. And if I go to small q, this term dominates. So the end result is that I get something that looks like this thing. So I mean, I just drew this to say if I multiply two Lorentzians and I try to integrate this, then only the skinnier one matters. But which one is skinnier depends on whether I'm at large q or small q. But it turns out large q here doesn't have to be very large, which is why it's interesting. So basically what you get is something which will go as 1 over q squared plus xi to the minus 2, where xi is this xi. So if you take the particular case where if you actually think of bacteria in a fluid, this quantity is 10 to the minus 2 in CGS units. And this is 1 second. So xi is as big as a millimeter. So you could, the presence of swimming bacteria in a fluid, so dirty water has velocity correlations out to a millimeter. The magnitudes may be small, but they're correlated out to huge sizes compared to the, compared not only to the molecules, but even to the bacteria. So it's amusing. So this is just, so I said long-range correlations. Okay, I didn't mean, it becomes truly long-range if you take this equation and forget about this. Right? Because the strict zero inertia, ignoring rho altogether, means that C is infinite. Not a surprise. So I think I'll stop. Oh, I actually have time. But I actually think I'll take questions rather than talk. I'm very tired. So these are just to summarize, what I've tried to do is to take you on a tour of the various dimensions of active matter as a statistical system and as a mechanical soft condensed matter system. I've shown you how statistical properties at the small scale have a profound influence even on the mechanics at larger scales. There are systematic terms in the macroscopic equations of motion which come from this minor fiddling with the statistics at a smaller scale. And I've shown you how it means that certain kinds of order are more robust and certain kinds of order are actually fatally non-robust, not even at the level of fluctuations, but even at the level of the linear theory. And I've shown you how there are rheological and correlation consequences of all this, and it's still a very live subject. And the thing I completely failed to do is to tell you anything about scalar active matter. My lecture planning clearly was too optimistic.